Hi everybody, welcome back to another My Tutor Online Schools tutorial. Today, GCSE Maths circle theorem, so carrying on down the geometry route. So this session is 1 hour long, so it will finish at 3 p.m. And it's led by me, Molly. You probably know me by now if you've been before, but I'm a second year, just finishing my second year computer science and maths student, and I've done over 200 lessons with my tutor. So hopefully that means I know what I'm doing. So throughout this lesson, make sure to use the Q&A and chat functions. Tell me if I'm going too fast, too slow, you'd like something explained again, another example, or so on. And I'd also encourage you to share your answers so that I can see that people are understanding it and staying engaged in that. So the plan for today is I'll go through each of the circle theorems and what they mean, and we'll do some example questions. Then there'll be a Kahoot, just like there was yesterday, this time with, I think there's 10 questions in it. And then right at the end, I'll do a little Q&A, make sure that we tidy up any last questions that anybody might have. So hopefully, a couple of people have said about doing a quiz at the start. Because I haven't prepared them for this week, they'll just be quizzes at the end. But from next week, I'll take that into account and do mini quizzes at the start and then a longer one at the end to see if we've improved throughout the session. So I have taken note of that feedback. I just can't do it for this week. So let's get straight into it. So to start off with, I just want to talk about a little bit of terminology that I'll be using. So luckily, there's a circle draw function here, so you won't have to put up with my horrific art skills. So the first thing is a couple of ones that you'll know is that all the way around the edge, that's called the circumference. And we all often talk about the center. And the radius is from the center to anywhere on the edge. And one key piece of information is that all of the radii, that's the plural of radius, are the same length. So that's kind of how a circle is defined. You choose a length and kind of draw that all the way around. The diameter is all the way across, so from one side to another through the center. So those are all ones that you're probably familiar with and have heard before. A couple of possibly new terminology is that, let's do this in a different color. If we draw a line here, let's draw a straight line. If we draw a line here, the line itself is called a chord. So it's basically from one point on a circle to another, not necessarily through the center. So from, nothing to anywhere. And the bits that it splits it into, so kind of here and this section, these are called segments. So a segment is, the way that I remember it, is it's like a segment of an orange, because it kind of looks like that with a straight line and then a curve. It's like, an orange segment. So that's what that's called. So if you hear me saying that word, that's what I mean. And finally, I don't think I'll be using this word today, but I will talk about it just in case. If we go from the center and draw two radii like that, the bit that it makes in the middle here, this is called a sector. So sector and segment can get a bit confusing, but you've just got to remember that a segment is like a segment in an orange. Cool. So hopefully those all make sense. That's just because I'll be saying these words throughout. Someone says we call that a pizza slice in school. Yeah, I always think about it like that. Everything linked to food. Someone said, well, we need a calculator today. Probably not. You might just if you want to speed up the mental maths, but we're pretty much just going to be working with angles. When we're going to be doing the circle theorem, so there's not going to be pi or anything like that. I don't think. So you shouldn't need a calculator, but you can use one if you want. So as I said, what I'm going to do is I'm going to go through the circle theorems one by one. I've got 8 here to go through. And I find this topic really interesting because the questions that you get, you can combine loads of circle theorems and find out loads about the angles of the circle that you're looking at. So let's go ahead and get started. So some of you might have seen these before, some of you might not. So let me know if I'm going at the wrong pace or anything. So the first two that I'm going to talk about, we start by considering a chord. So like this. And if you take that chord and you, oh, that's the other word that I didn't say. When we have a chord like this, this bit here, so like a section of the circumference is called an arc. And what we say is that this angle here, let's call it x. In fact, I'm going to call it 2x for reasons that you'll see in a moment. 2x is the angle subtended by the arc. Some fancy maths words. Mathematicians like using long words to make themselves sound smart. So this angle is the angle subtended from this arc here. But basically what it is that we draw a chord and then draw some lines coming up to the center. And then if we draw some lines, I'll choose a different color, going up to any point on the edge, it doesn't matter where, then this angle here is half of that. So the kind of phrasing of this one is that the angle at the center is twice the angle at the circumference. And the key thing that you've got to remember from that is they've got to kind of come from the same 2 points. They have to be subtended from the same arc. Fancy words, but basically it just has to look like this diagram. So I always remember this one as kind of like the arrow theorem, because if you ignore this bottom line, it looks a bit like a cursor, like a mouse cursor. Yeah, so whenever you see this shape, immediately think about that. Again, this is me just going through what all of them are, but we'll do a lot of practice, so you'll see these questions in practice once we go through them. So don't worry if you're not fully understanding it now, basically. Okay, let's have a look at the next one. The next one is really similar, and you can actually understand it by looking at the previous one. So again, with this one, if I'll always draw my circles like this, but we don't actually always need that center bit. In fact, let me screenshot that. Cool. Again, if we have a chord, and this time we're going to draw an angle at 2 different random points on the circumference. So say here and this one and this one. So just kind of anywhere on there, as long as they reach the circumference. Then this angle and this angle are the same. And the formal wording for this one is angles from the same chord are equal. And you can kind of see that from this first one, because remember that we said that the angle at the center is twice the angle at the circumference wherever you draw this at the circumference. So you can kind of see from that the proof that this does actually work. So where I could have drawn one here or right over here, but if they come from the same chord, then they're going to be equal. Someone said, when you put 2x, do you mean x times 2? Yeah, exactly. So if this is x, this is 2 times whatever that x is there. Okay. Let's go for the next one. So this next one has another kind of horrible bit of wording with it, and that is, I'll write it when I write it out. It's called a cyclic quadrilateral, which I think sounds horrible. But once you know what it is, you can show off and sound fancy. So all this means, so a quadrilateral is just a 4-sided shape, and a cyclic quadrilateral is one where those 4 corners of this shape are points on a circle. So if I choose a color, so we can draw it however we want. It can be a a square, a rectangle, a trapezium. I'll make it this kind of shape like this. So that there is a cyclic quadrilateral because you can see each of the corner points lie on this same circle. And the theorem about this is that the opposite angles in a cyclic quadrilateral add up to 180. So I guess if this one's x, in fact, why don't I'll color code them and then, oh yeah, I know what I'll do. I'll just label them different things and we can say things about them. So we'll call them A, B, C, and D. So the kind of informal way of writing this is that, so angle A plus angle C is 180, and angle B plus angle D is 180. And as I said, with all of these, there's a formal way of writing these. So this one says that opposite angles in a cyclic quadrilateral, so that's how you spell that, add up to 180. So again, this is only true in a oh, someone said, could you re-explain which bit are you referring to, like this one or the previous one? Just sorry, just because I don't always see them as soon as you ask them, just let me know. The last bit about the cyclic quadrilateral. Oh, the previous one, this one here. I'm not 100% sure which bit you mean. Oh yeah, this one here. Okay, cool. Sure. Yeah, if you ask me to re-explain something, just be like specific about which one, because I don't always see them straight away, so then I don't know what you're referring to. So this one says that if we have a chord here, and we just kind of draw lines up to the circumference from the two ends of the chord, they'll form the same angle. So if you want to kind of see it again, we could maybe draw them up to say here. And as long as we draw them from that edge there, this will also be angle X. So, you know, if this gives us 30, then this is 30 and this is 30, and wherever else we draw them, they'll always equal 30. Okay. Yeah, so that's that one. That's the cyclic quadrilateral one. So theorem 4, as I said, out of 8 that I have here, is this one. So this one, we take a line and draw a diameter. So that's something from one side to the other that goes right through the center. And then we connect it up to the circumference in any place. It doesn't matter at all which place. And then can you see here that this has formed a right angle? So that wouldn't have mattered where we'd drawn it. If we'd decided to draw it over here, it still would have formed a right angle. Now, the formal way of writing this is that the angle of the angle in, I think, a semicircle is the correct phrasing, is a right angle. And that's because when we draw this diameter, we're chopping it in half. So then this section here is a semicircle, and it just, by the angle of it, means you just bring those edges here and it forms a right angle. So it's kind of like the previous ones, but instead of just a random chord, the chord is specifically the diameter, and that forms a right angle when we draw it to the edge. Someone's asked if this lesson will be uploaded to the YouTube channel. Yes, it will. I'm not sure when, I don't know how quickly they are, but it definitely will be. Someone asked, just from this one, what's the cyclic quadrilateral? Again, it's a four-sided shape that fits exactly within a circle. So it's not like smaller than or bigger than. The edges exactly are on the same points of the circle. And we'll see more examples of these, as I said. Okay, so we're halfway through them now. The next two both involve the tangent. So I'll explain what that means, don't worry. So a tangent to a circle is a straight line that only touches the circle at one point. Now, I think I've talked about this before, and it's a really, really difficult concept to kind of think about. But if you just imagine zooming in and in and in until we're on like a microscopic level, it just brushes it at kind of literally exactly one point. It's kind of a Yeah, a weird one to think about. Someone's asked if there's a Kahoot. Yeah, there will be, probably in the last 20 minutes. And someone said, do we need to know all 8 of these for GCSE? Yes. Okay, so I'll draw an example of what a tangent looks like here. So these are quite difficult to kind of draw. But if you imagine it like that, so you see here, oh, that wasn't too bad actually. That wasn't actually too bad. If we zoom in and in and in, here it still looks like it's touching at multiple points, but if we zoom in and in and in again, we'll see that it's just grazing it at that one point. So that's what a tangent to the circle at that point means. And then if we draw, let's do this in a slightly different color, a radius, so just from the center to the point where it is a tangent. So it's all about, we're focusing all about this point here. So if we draw a tangent to that point and a radius at that point, where these meet, it forms a right angle. And I think you can kind of see that from how it's drawn on there. So the radius and tangent at a point form a right angle. That's the kind of formal way of phrasing that. This one doesn't like have any specific, someone's asked what's it called. There's no like specific fancy name for this one. The other thing, if you're a maths nerd like me and you find this sort of thing really interesting, on Bite Size, if you search for GCSE Maths Bite Size circle theorems, they actually prove all of these. So go through like the mathematical proofs for you by drawing other bits. I wish I could go through them, but it's not on the exam, so there's no point. You know, I'd rather tackle some questions, but if you are interested, I'd really recommend that. It might make them make a bit more sense as well. So that's on Bite Size. Okay, so that's that one. Another one about tangents. So if we have a circle and we pick a random point that is outside of the circle, so let's just choose here, then if we can only really draw 2 tangents to the circle from this point. So one is going to be kind of going in this direction and the other one going in this direction. And what this theorem tells us is that the lengths of these are the same. So the length from exactly where it hits on the tangent, so these dark blue lines that I'm drawing, those are exactly the same length. So if this is of length L, this is of length L. So that's what that one tells us. Okay. Right, 2 more to go. We've almost got there. The other thing is, I think when I learned this, I found it really overwhelming, thinking like there are 8, how on earth am I going to remember them all? You're never going to be asked just like state all 8 of the circle theorems. If you just practice them enough, they become really second nature. Like I had to look up what they all are, because even though I know and understand them all, I can't just list them off the top of my head. So don't worry, you don't need to be able to do that. You'll see once we start doing questions, you can just kind of spot, oh, that's that theorem, and so on. Someone said, what's the proper terminology for this one? Oh yeah, you're right. I'm sorry, I didn't write that one out, did I? So it's tangents to a circle from a point are of equal length. That's the proper terminology for that one. Okay, so 2 more. Okay, this one's pretty cool as well. So we start with a chord like this. Now, if we draw a radius, or like the start of a radius, it basically goes from the center and hits it at a right angle. So, for example, on this one, it starts at the center and hits it at a right angle. I'll do it the best I can. It's very difficult. Like that. So this has been hit here at a right angle, then that has bisected the chord. And what that means is that if we look at where it's been hit here, the length of this half up to where it touches it, let's call that L, and the length of this half, that's also L. I think this one is slightly less common. I haven't seen it as much in questions that I've done, but yeah, I think it's still useful to know. So hopefully that makes sense. And the proper wording for this one is a perpendicular line bisects the chord. From the center, bisects a chord. Because bisects, bi means two, so it splits it into two equal parts, basically. Yeah, someone said these diagrams look weird. That they do, but yeah, you get used to kind of seeing them the more you do. Okay, so we're on the last circle theorem, and this one has a name, which is very exciting. I remember hating this one because it seemed confusing, but it's actually not too bad. So this one has a name and it is called the alternate segment theorem. Horrible name. It doesn't tell you that much about it, to be honest. It's just useful because when you answer circle theorem questions, and you'll see when we go through, you have to justify everything you do. You have to be like, this angle is this because the angle at the center is twice the angle at the circumference, and so on. So this is nice because you can just be like, by the alternate segment theorem, rather than writing out anything longer. So what this says, gosh, let me make sure that I get this right. This one's quite difficult to remember, so I might have to look it up, but I think, so if we draw like this into like a triangle, then, okay, I might have to get up an image of this one. I think this might tell me on here. Yeah, it's like this. There's a tangent in it, that's why. I always struggle to remember this one. Let me redraw those. So if we draw a triangle with more like a point at the bottom, and then a tangent at that point. Oh gosh, that's not good. It's so difficult to draw tangents. There we go. Then this angle, this green one, is equal to this one. And this orange angle is equal to this one. So the reason that it's called the alternate segment theorem is because this angle here is, if you think about this being a segment, this section here, and this being a segment, then this angle is equal to the angle in the alternate segment to it. It's kind of weird. You don't have to, yeah, I think this is the hardest one to remember, but normally it's fairly easy to spot because it looks quite distinctive. The formal wording for this is kind of horrible, and I wouldn't advise, like the other ones, I think the formal wording is useful. So I guess this one is technically the angle between a chord and a tangent is equal to the angle in the alternate segment. But I don't think that's very descriptive. I don't really think that tells you much. So I just try to remember this diagram for this one. Someone's asked me to re-explain this one. Sure. So basically, we take a tangent, and then from that point, we draw it up into a triangle. Draw up two lines and connect them. It doesn't matter where, because obviously changing what it looks like changes then the angles that are formed. And then if we draw an angle here, it's the same as the opposite angle kind of in the opposite top corner of the triangle. So the one on the right down here is the same as this one. The one on the left down here is the same as this one. So if you want a better diagram, you can have a look here at this one, alternate segment theorem. This is on Maths Made Easy, by the way. It kind of summarizes them all. So this is maybe a good place to look. If you need to be reminded. So yeah, this is a weird one. This was definitely my least favorite circle theorem when I did it. So hopefully that makes sense. And when we go through some questions, you'll see. Okay, so a couple of people told me that I'm going quite slowly. I just want to make sure, because this is the most important bit, is knowing what the theorems are. Now I'll jump into some questions. So hopefully it'll be more at everybody's pace. So yet again, surprise, surprise, I'm getting these from Maths Made Easy, my favorite website to find maths questions. So this is what a typical question would look like. So some of them are easy like this, where it's just one. Sometimes you have to apply 2, 3, or even 4 circle theorems, one after another, to work out what the answer should be. So normally it's got a wordy bit that tells you what you can see in the diagram. So points A, B, and C are all on the circumference of a circle, and O is the center. We can guess that from the diagram, but they have to tell you. Calculate the angle X, giving your reasoning for each step. So yeah, someone's asked for time to answer it first, so go for it. I'll give you like 30 seconds to a minute to answer this one, so shoot me over your answers once you've got them, and then I'll go through it. Remember to give your reasoning as well. Cool, a couple of people have already got it. Okay, cool. 5 or 6 people have already got that, so that's fantastic. Okay, cool. So for this one, yeah, a couple of people have said that they have no idea as well, which is totally fine. These are really hard to start with because you're not used to spotting what the theorem is that you're supposed to be using. So maybe to start with, if you want to maybe have the Maths Made Easy example, what you need to know section open, or like have some notes in front of you with what the theorems are. So for this one, the theorem that we're going to be using is, let me try to get up my diagram of it here, is this one, the first one that we went through. So the angle at the center is twice the angle at the circumference. So we can see here, we can kind of put a line on ourselves if we want to. That if we imagine a line here, this angle here, 98 at O, is the angle formed at the center, and X is one of these angles formed at the circumference. So what we write as our answer is X equals 49, because the angle at the center is twice the angle at the circumference. And I think this is probably a 2-mark question. Yeah, 2-mark question. One's for getting it right, the other is for the explanation. Yeah. So this is, I'd say it's a simple one because it's just one step, but it's not simple because you do have to spot it. It's just, I guess, simple in terms of its fewer steps to do. So let's have a go at another one. And again, I'll give you time for doing it. So let's have a go at this one. So again, we've got the same format as before. So we've got some information that tells us pretty much exactly what we can see from the diagram. So A, B, and C are on the circumference, and this line passes through the origin, O, so the center of the circle. So that means CB is a diameter, and we want to calculate the angle X. So there's actually going to be 2 steps to this one. So have a go at answering this. Someone's asking about how is it 49 from the previous one. That's because it was half of 98. because it was the circumference. I'll do another one. Someone's asked me to re-explain. I'd rather stay on this screen for now so that people can tackle this one. But I'll go through another one similar to the previous question, so don't worry. Cool. A few people are getting it already, which is fantastic. So remember, even if you don't write it down and send it to me, because I know that can be quite time consuming, think about what your reasoning would be, because a lot of the marks in this come from the explanation. It's kind of a weird section of maths where it's a lot more wordy than other sections, which I think is good, because it's just, you just have to prove that you understand what you're doing, and it's kind of like free marks. Okay, perfect. Quite a few people have got it now, so I'm going to go through this one. Okay, so one step is a circle theorem. The other step is something that we know about triangles. So the first thing is that we're going to use, let's see which circle theorem it was, this one here. So the angle in a semicircle is a right angle. So if we have a diameter and we join it to the edge, it forms a right angle for us. And that's what this is here. See, we have a diameter, we've joined it to the edge at this point A, therefore this is a right angle. So that's the first thing that we say. We say angle CAB is 90 degrees because the angle in a semicircle is a right angle. So that's the first step that we write down. Now we see that this is a triangle, and the angles within a triangle add up to 180. So the next bit that we do is we say 90 plus 32 is equal to 122. Therefore, x is equal to 58 because angles in a triangle add up to 180. So there you go, just those three little steps. And it's just a tiny little bit of explanation, and you get so many more marks. So a lot of people got this one right, which is really, really promising. So well done. I think, yeah, the main thing to pick up from this is writing out the explanation. Somebody said, can you go back to the page where you drew the theorems? I'd rather kind of move on with the questions, but if you just look them up, there are lists of them everywhere. So you can look at those theorems then whilst you attempt them. Okay. Let's have a go at another from on here. Whoops. Yeah, so I think this diagram, when you first look at it, looks quite overwhelming. That previous one, by the way, was 2 marks, as is this one. I think that previous one should definitely have been more marks, actually, because it was 2 steps. But okay, so again, we start with some explanation. A, B, and C are on the circumference. O is the center. Calculate the angle X, so this one here, giving reasoning for each step. So I think this one's very difficult. Because there's something that you need to spot, which I think is quite difficult to spot. So I'll give you a couple of minutes to have a go at this one and see if you can get it. It doesn't, just kind of a hint, this doesn't actually use any circle theorems. It just uses some fact about circles. Okay, one person's got it right so far. Okay, I'll give you a clue because this is a difficult one. Yeah, so someone's asked a question which is exactly right. So AO, BO, and CO are all radii of the circle. So if they're the same length, think about what that means these triangles are. What type of triangles are they? And what does that mean about the angles? So have a think about that and then see what you think. I'll just give it 30 more seconds and then I'll go through this one. So don't worry if you... Yeah, brilliant. Someone asked who got it right. I'll reply to people if they get it correct. I reply saying that it's correct. So you'll know if you do. At least on the chat one, I will. Okay, I'm going to go through it now. Someone else just got it right there. Okay, cool. So yeah, the key thing to notice here, as I said, it's sneaky because it's not a circle theorem. It's just using some fact about circles. So the key thing that we're going to use is the fact that if two of the sides of a triangle are radii, they're the same length. Therefore, these triangles are isosceles. So we first of all think about the fact that this one's isosceles. So this kind of triangle here, AOC. That means that this little section here is 22. So this bit here is 22. So a lot of you are spotting that. So that's the first kind of bit of our explanation that we're going to write, is that angle ACO. So the way that I label the angles, by the way, is kind of how you draw it. So A to C to O makes that angle. So that's what we say. Angle ACO is 22 because triangle ACO is isosceles as two of the sides, or in fact, we can be more specific, as AO and CO are both radii. So that's saying why that's 22. Then similarly, if I switch to another color, this one and this one are the same, so BO and OC. So that means that this triangle here is also isosceles. So this whole angle here must be 67. So we can say angle BCO is 67 because triangle BCO is isosceles as CO and BO are both radii. So we're actually using the same argument, just kind of applying it twice. And then if that whole angle BCO is 67, we say therefore X is 67 minus 22, which is 45. And there you go. That's that question fully completed. Okay, cool. So well done if you got that one right. That one was quite tricky to spot. So well done. Let's have a go. Another. So this is one where we've got some tangents involved. Okay. Just want to make sure. So I'm just going to do this one question and then we're going to go to the quiz. So, okay. Points A, B, and C are all on the circumference of the circle. We know that O is the center, makes sense. DA and DC are tangents to the circle, and angle CDO is 22. So all this tells us, it looks quite wordy, but it's telling us everything that we can just see on this diagram. So we want to calculate this angle X, giving reasons for each step. So this one is quite tricky as well. So give it a go. I think this should be definitely at least 4 marks for that. Yeah, 4 marks. So I'll give you a minute or so to have a go at this one. Okay, so I'll just give a hint. The first thing that you're going to want to do is use one of our theorems about tangents. And what does it mean that this angle and this angle is? And then have a think about how we can work out this angle here. So I'll just give you, say, 30 more seconds or something. Okay, I'm going to go through this one now just because I'd like to get onto the quiz. So the first thing that we do here is we know that this angle and this angle are right angles. And that's because of our theorem that says when the tangent meets the radius, it forms a right angle. So that's what those are. So that's the first thing that we have to write, is we say, angles OAD and OCD are 90 because they are angles where the radius meets the tangent. So that's justifying that. And then this bit, the way that I would justify it, and I think it's the only way that you can, actually uses congruent triangles, which we haven't gone through yet. But it's basically just where a triangle is the same. And we can say that this length is the same because they share it. These lengths are the same because they're both radii. And here, there's a theorem that tells us that the lengths of the tangents from a specific point are equal. Therefore, these two triangles are the same, which means that this angle is also 22, and these two angles are going to be the same. So we can say ADO is 22 as the triangles AOD and OCD are congruent. You might have to explain that a bit more, but I'm going through it a bit more quickly. Therefore, angle COD equals angle AOD. So here I'm talking about this angle and this angle. I'm saying they're the same, and they're both going to be equal to, and are equal to, well, again, angles in a triangle, we've got a 90 and a 22, which makes 112. Subtract that is 78. Sorry, 68. 68. Therefore, angle AOC, so that big angle there, is 136, I think. So that's what this big angle here is, 136. And then finally, this here, so our angle X is going to be half of that based on our circle theorem that we did right at the beginning. So X equals 68 because the angle at the center is twice the angle at the circumference. And a lot of you got that, which is really, really good. So there's a lot of steps that you can see where you have to explain it again and again. Someone asked how I got 136. That's by doubling 68 because each of these bits is 68. So the whole thing's 136, so this is 68. So well done if you did that. Now let's hop on over to the Kahoot. So get the app or whatever up on your phones or your laptop, and have a go at this Kahoot. So these questions were from a quiz that I found, which I'll put credit for on the description in here. So there you go. There's the, oh gosh. I've muted the site, but it's still playing music. Make it stop. That's better. Cool. So hop into this. So there are 40 of you now. So I'll wait until there's hopefully around 40 people in here. And we'll get started. Let me know if you're having any issues getting on. Wow. Someone's David's maths joke. There will be one. Don't you worry. Thank you. Whoever called themselves No Bully Molly. Appreciated. Oh, yes. The Molly love. Big up. Okay, is anybody still waiting to come in? I know that not everybody connects to these. Okay, someone says that they're still waiting. Loving the different capitalizations of my name. Incredible. Okay, is anybody still waiting? Okay, I think I'll start it now because if you haven't had a chance to log on, oh gosh, okay. If you haven't had a chance to log on, then we can just you can just like play along and write down your answers or something like that. So I think that's everybody. Yeah, as I said, there are 40 people here and there are 34 in here, so that's pretty good. Lots of people. Okay, I'll get started. I want to get it done. I'm really sorry if you haven't managed to get in yet. So let's go. Okay, there are 10 questions. As I said, not mine. I'll give credit to the person in the description of it. So we'll have a diagram. I hope they're good enough quality. What's the value of the angle x? So I think I put a minute on for each of these. I might have put a bit longer if they were harder, but I might have to make the times a little bit quicker just so that we get everything done. And somebody wanted me to re-explain that last example question, so I'll see if I have time for that. Okay, so I think that's everybody's answers. Yeah, brilliant. Loads of people got that right, the majority. So the thing to spot here is that this one at the top is a right angle because it's the angle from a a semicircle. And these two are both radii, so it's an isosceles. So if that one's 90, the other two have to be 45 because they've got to be equal. Okay, next one. Oh, I didn't press next. I'm sorry, these pictures are not very good quality. This says 63 down here, and X is the one at the top. Cool, well done. Again, majority of people got it right. So the thing here was that this triangle on the left is isosceles. So this angle down here is 63. They've got to add up to 120. 180. So the top angle here is 54. And then from the theorem that says angles from the same chord are equal, x is also 54. So here we've got two angles to look at, C and D. So we want to know what each of them are. Okay, I want to get through it all, so I'm going to skip to the end. Sorry if you didn't get it in. Okay, so that one seemed quite tricky. Not everyone got that one. So this one here, it's just one circle theorem, but it's one that we didn't do a practice question on, unfortunately. So this is a cyclic quadrilateral. So it's a quadrilateral and each of the points are on the circumference of the circle. So opposite ones add up to 180. So D has to be 78 to add up to 180 when paired with 102. And similarly, C has to be 63. So that's what that one was. Okay, again, we've just got back to one angle to find here. Speedy answers coming in here, that's good. Excellent, well done. So that's the vast majority of people got it. So this is where the angle at the center is twice the angle at the circumference. We've seen it 2 or 3 times now. So if this one's 100, this one's 50. So well done. So that's done to the scores. Ooh, stayed the same. Okay, halfway through, what's the value of the angle marked X? Yeah, well done, guys. Really, really good. So the first bit that we use is that this up here on the top left is the angle in a semicircle, because we've got the diameter coming across, so that's a right angle. So those two add up to 133. Angles in a triangle have to be 180. So this one here must be 47. So well done. Again, we've got two angles now to have a look at, angles C and D here. So this is using two different circle theorems for each of the for each of C and D. Okay. See? Yeah, brilliant. Most people got that right. So to find C, it's everybody's favorite. Angle at the center is twice the angle at the circumference. So it's double 71. So it's 142. And to find D, this is here as a cyclic quadrilateral. So they have to add up to 180. So a few of you thought it was equal. It's not. It's that they add up to 180. So that's 109. 10p Asda bag climbing. So what are the values of the angles marked A and B? Again, we've got 2 more to find in here. Just while you're answering this one, I don't think I have time to re-explain that final question, just because I think this will only just finish at the end. Sorry about that, but this will be recorded, so you can go back and have another look at that final practice question. Sorry, that's poor timing with the quiz on my part. Brilliant. Well done. Again, vast majority of people. So to find B, it's twice the angle at the circumference, so it's 114. And to find A, it comes from the same chord, so it's equal to this angle of 57. Brilliant.